Hi, my name is Will Scott, and I'm a member of the data systems team at Protocol Labs. We work on the data layer of a bunch of the data transfer protocols and stacks in the interplanetary stack that Protocol Labs helps maintain. And so this talk is looking at content routing and how we find content in both Filecoin and in IPFS, and more broadly, what that part of the system looks like today, and some of the work that we're doing to try and help scale that going forward. And so this talk is looking at content routing and how we find content in both Filecoin and in IPFS, and more broadly, what that part of the system looks like today, and some of the work that we're doing to try and help scale that going forward. So I'm going to start by talking about where content routing is today, and then I'll move sort of up the stack through this talk so that by the end, I'm talking more about how the providers who have content are providing that content out to the network and those protocols. So today, from something like IPFS, content routing happens through a DHT. And what that means is each piece of content, which is identified by a CID, a content ID, which is the hash of that content, is the item that is both being requested and being published. So people who have data that they want to make available to other IPFS users will publish that data into the DHT by finding the around 20 appropriate nodes that make up the mesh and putting a record into them, indicating that they have this content. And so it is a abstraction that looks a lot like a key value store, where the key is this CID, the hash, and the value is that publisher, that location. Part of the way that the DHT works is that in order to prevent stale records, so some publisher saying that they have something and then going away, but you still getting that answer a long time later and not actually being able to connect to them, is that records that get put into the DHT expire after a day. And so publishers who want to keep content available in the current IPFS world republish every day to sort of indicate they're still alive and still providing that content. This has a couple scalability limitations, right? The DHT setup grows very well if the amount of content grows with the number of participants, right? So if you have something that looks like a blog, or everyone bringing their own library of data, and so as more users join and the DHT grows larger, the data can also increase linearly at the same rate. But there's other sorts of quantities of data that are just too big for a DHT in this sort of paradigm, that they'll really overload all of the nodes that are participating in the DHT. So if you imagine wanting to do something like a search index over a lot of data, so think a big library of content, maybe web search archives, other things like that. It just means that there's so many CIDs that each individual participant in the network, unless you also grow the network a huge amount at the same time, will end up having more records than they really can meaningfully supply. And it means that the amount of bandwidth for the publisher who's trying to keep all of that data available gets very large. So we start facing these larger scales of data with Filecoin, and are looking at what is the sort of next iteration of this protocol that we can use to deal with this increased scale. So the focus from my perspective is the thing we want to get right is the protocols, and we'll figure out the ability to iterate the specific mechanism at a different rate if we've got good protocols on the two edges of this. So if we have a good protocol for publishing and a good protocol for requesting and finding data, then we can allow ourselves some additional flexibility and freedom to experiment with different specific implementations of content routing. So what I'm going to talk through next is sort of the thoughts on where we go on those two. So the first is content routing. And so this is a user looking for a specific CID. And we already have an interface in IPFS that is roughly what we might want, which is when IPFS needs to find data, it makes a request that is the content routing interface. And it is, I want to find providers for a CID, and I get back asynchronously, and this is the Golang terminology, a channel that over time gives me the addresses of people who may have that data. And so what we'd like to do is take something that looks a lot like this and expose it over a network interface so that I can have some other external system, either as some other program on the same computer, as a library, or as some remote service, they can serve to implement this interface. And so I think we'll start to see this and some abstraction that looks a lot like this coming to a set of clients that are able to retrieve and provide data from some mesh of IPFS and or Filecoin, and more broadly for content address things. So that's our thought of, what is this simple client side of this interface? Okay, so then what do we do to actually implement that is the next question. And the work that my team is pursuing right now is an indexing solution where we're trying to say, well, okay, can we just make something that happens to know the answer to all of these queries? And this is building on a bunch of great work that's happened over the last couple of years. There was an initial implementation of a storage system that's optimized for these CID hash-based keys called Store the Hash that Volker made, and that has then been ported to Golang, and that we're now using as the basis of a network index system that we're calling Store the Index. So let me give you a brief walk or sense of what that's doing and how that's actually working. So it takes a CID and it uses some bytes of that CID itself, which it believes are generally random, right? Because it's a hash in general. And so what it does is it first uses some bytes of that CID to decide which bucket to look at, right? So it has a bunch of different buckets in memory, and those buckets will point to index files on disk that grow. And so it will use a specific subset of bytes in the CID to just determine first a bucket that then points to an index. And then it will use another set of bytes in the CID, again, that it already has, to determine an offset in that index file on disk that the record for that CID should end up in. And so then it'll make a read of that index file at that offset. So this is the first read on disk, and that'll give it a record that has a relatively small, comparatively, number of CIDs that match both that bucket and that index offset. And what it will get in that record that it reads from disk is a pointer that hopefully includes that CID if it knows about it, and the relevant metadata entries for that CID. And so then it will do reads to get those specific metadata entries. And the metadata that we're imagining ends up being stored for a CID is the provider who has it, where they are, the multi-address. So this is this full address info that we've talked about. Basically, it's how to find them. And then also, what protocol they're talking about and relevant metadata that's protocol specific. So how you actually go about retrieving the data from that provider. And this gets, this is one additional level of complexity than what we have had previously, because now we're having multiple data transfer protocols, both BitSwap and GraphSync, as potential data transfer options. And we expect that there may end up being additional ones. And that's part of the extensibility and flexibility here. The nice thing about this setup is that there's a fixed number of reads from disk that happen, regardless of how many CIDs end up in the database. You do one read in the index to get a record chunk, and then you do a read to get the specific metadata entries that you want. The reason we do the extra lookup on metadata is because we expect that there is sort of, for a given provider, there's many CIDs, right? So if you think about a Filecoin deal, that's 32 gigs typically of data, which has many CIDs within it. And all of those, the process that you should then use to retrieve is the same. And so we can deduplicate and spend a lot less disk resources if we do that deduplication. But it means that there's only 2 to 3 reads from disk for a given CID, regardless of how many CIDs are in the index. And so that means the only thing that we're really having to scale is disk usage. But we end up retaining a relatively low latency. We're optimistic this ends up being, order of 5 or 10 milliseconds to answer a query. Microseconds. Random access disk seeks, even as the database of indexing gets very, very long. Okay, so you've got this abstraction of this library that's able to do, individual indexing requests. It can answer for a CID who has it relatively quickly, and it should be able to scale. But that's part of the story, right? We've still got to answer, how does this indexing component actually learn about all of these CIDs? And then I want to talk a little bit about how we see this sort of evolving in the future. Now that we've got interfaces right, this is one solution, but it's certainly not the be all end all. I'm sure that there's already a lot of questions in your head about, okay, so if there's this centralized thing, well, aren't we building a decentralized web? And yes, of course we are. Okay. So the other interface, and this is, I think, right now, the focus on the thing that we want to get right and the protocol we want to get right, is ingestion, which is how do we learn what data various storage providers, be they Filecoin or large IPFS nodes, have, and get that reflected in the network index. So the current thought is that what we're expecting from storage providers is that they will have a hash chain of basically advertisements of what content they have. And they'll expose this list of advertisements and the CIDs in those advertisements as a thing that network indexers can get from them. The reason that we're having this as a sort of hash chain of advertisements that are signed by the storage provider is this is part of that extensibility, which is, it's not that the storage providers are pushing or just sort of saying, I've got this data, which would not be, immutable, would allow them to provide potentially different views of their data to different indexers. We want to make sure that the sort of expectation on storage providers is they have one view of what data they have, and that is global, so that as other network indexing solutions come in, they can also use this protocol to get the same view into what content is available in the network. Okay, so what does it look like as either a new Filecoin deal happens for a provider, or they through some other means get an additional set of CIDs? Well, the first thing that they'll do is they'll take those CIDs, they'll make the list of them, and then they'll make an advertisement that points to both that list of CIDs and the previous advertisement. And that'll be their new sort of head of what content is available for this provider. The provider then advertises this, and it's a best effort gossip sub, basically advertisement of, I have new data available. And this is on a topic that network indexers can listen to so that they can get notifications for lower latency polls from storage providers who have new data. In addition, we expect that the network indexers will sort of keep track of known storage providers and will pull them on some regular basis to see if they have new content. So the gossip sub is a way to lower that latency in most cases, but there's a sort of a fallback to make sure you are keeping everything in sync. Once a networker indexer sort of learns about this and adds it to its queue of providers that it needs to get updates from, it will use GraphSync to pull first that advertisement and then the list of CIDs that it does not yet have. And there's a couple of reasons for doing it this way. The GraphSync means we only get the portion of the DAG that we do not already have. So it gives us this partial resumption of, oh, I already have older advertisements, I'm not going to re-get them. We also expect that there's a bunch of deduplication in the SIDs, which is a deal that is made to Filecoin is likely made to multiple providers. And so by having this sort of structured through this IPLD setup, the indexer will only have to fetch that from one provider, not from all of them, and not duplicate that work because it knows, oh, this is the same list of CIDs that I've seen in other places. So the indexer pulls that and then adds to its index that these CIDs are now provided by this provider. Okay, so the advertisements either introduce a new set of CIDs or retract and say, I am no longer providing some previous set of CIDs. Those are sort of the two basic deltas. And then in that advertisement layer, it says what metadata and protocol should be used to retrieve them, right? Because we expect that for some large set of CIDs, you've got one sort of mechanism. So if you end up as a storage provider having different protocols or whatever, you would do that through multiple advertisements, each with the smaller set of appropriate CIDs that match that metadata. Other metadata that you might imagine is things like, is this available for free retrieval, or is it going to cost Filecoin to do the retrieval? Okay, so an indexer has the SID, maintains it, but let's talk now about sort of what that expectation of the growth and sort of evolution of the index is. So we're doing one index, right? there's one thing which is like, okay, as this scales, what's the plan? And there's two ways that it can scale. You can either scale in terms of having a lot more queries, or you can scale in terms of having a lot more data. And hopefully we scale in both. As we get more queries, likely what you want to do is have caches of recently queried CIDs that end up closer to clients, right? And that takes load off of the actual primary index, because many of there will be a small number of CIDs that are requested many times, and many CIDs that are only never requested at all. So you can pull that frequently queried head into a set of caches that are closer to clients. The index itself is then limited primarily by that growth, right? Like as those disks get really big, that gets expensive, or it can't pull from the growing number of storage providers in a reasonable way. And so you can imagine sharding it, where you end up with regional partial indexes. So there's some index that looks at storage providers that are in North America, and a different one that looks at storage providers that are in Europe. And you can probably scale that to another order of magnitude, potentially just by sharding across regions. And then the local caches will send out sort of parallel requests back to these multiple different partial shards, maybe potentially preferring the local ones because they want to connect clients with data that is closer to them by default. But if that fails, then they fall back to further away shards. And that way you've got a set of fairly tractable extensions that likely allow you to keep scaling this for a while. Okay, but that's all still within the scope of a single trust administrative region, right? There's some operator that's operating this whole system. And this is why the focus initially is on the protocols of both content retrieval on one side and storage provider ingestion on the other side, which is we don't want to be making the only network index, and we don't want to be running the only network index. So there's a few different sort of thoughts here. One is the expectation is pretty quickly we'll end up with federated replicas where other entities also are running network indexes. And that gives you a couple options. One is that clients can query from multiple providers' indexes and can check them against each other to make sure that no one is lying and that these are all sort of operating in sync and have similar views into providers on the network. The other thing in the provider ingestion interface, right, is that you've got this now attested chain that's not mutable from each provider saying what data they have. And that means you can do a dispute process where if the index responds to a query either saying the provider doesn't have it when the provider does, or vice versa, saying a provider has something that they don't, you've got a process where you can show the attested record from the provider and the response from the network index and say, look, these don't correspond, and you can figure out who is lying or who has provided incorrect data based on the underlying provider records from the provider. And so that means you can now introduce a whole set of incentive games where you make it irrational for a network indexer to not provide the standard view of the network. So that moves us closer towards an untrusted or supporting potentially Byzantine indexers, where the indexer itself can be malicious, can provide incorrect information, because you've got a dispute resolution process for those who have grievances. We're trying not to specify fully a protocol for moving towards untrusted. Either, how would you have sort of hierarchies where people who are offering network resources end up slotted into this, because that will likely depend and be interrelated with a larger set of incentives that need to happen with retrieval that are still sort of evolving, right? So you could imagine schemes, for instance, where when I do a retrieval, there's some sort of finder's fee where the indexing subsystem or the set of indexers that help me matchmake to a given provider gets a percent or of the retrieval cost, or gets some fee for doing that finding. And maybe there's indexes that are fast but only have some of the content and they charge less of a fee. And then there's other more expensive to run indexes that have all of the data but charge a higher fee. So there's potentially some sort of market here. And before we've fully understood the set of constraints and incentives that are useful in structuring that market. We don't want to sort of over specify it. So we're expecting that evolves, and that the right thing in this iteration to get right is those two interfaces, so that we can then iterate and change what component actually exists as that networking interface without having to keep updating the protocol that either the providers or the clients are speaking. So to finish off, we're working on indexing. You can see the code, the network indexer that stored the index. There's a reference provider at index reference provider. And this work, you know, I'm not doing this work, but the whole data systems team that you see in these pictures below is really the ones to credit for this. So with that, thank you. I'm happy to take questions on Slack or through any of these various protocol labs messaging channels, or you can reach me at Will Scott. Thank you.